Hello. I'd like to spend a little bit of time talking about mistakes. So it's the start of a new school year. You're going to have teachers say things like, in this class, we value mistakes. We like when you make mistakes so we can see your thinking. And what I want to do is spend some time trying to convince you that that is not a helpful statement, and that the use of the term mistakes or something similar is actually counterproductive to learning. Even when a teacher tries to use it in a way that tries to normalize mistakes, that word itself needs to kind of be taken out. So, it's not just the word mistakes, but anything that implies that there is a binary system where there is a right and a wrong answer. You're going to end up relying on authority of the teacher and of the situation in a way that's not healthy. So I want to break that down for you, what that means a little bit. My claim here is that everything that you can say or explain or do or find a response to will be useful or true in some situations, but not in all situations. And that when we go to learning, we want to look at under what conditions and assumptions is this helpful or productive or useful or correct, and under what situations is it not. And that most of the good abstract learning that takes place is by evaluating those conditions. So let's look at an example. So in my chemistry class a couple years ago, we looked at a hydrogen emission spectra. And if you're unfamiliar with hydrogen emission, basically when you put 10,000 volts across some hydrogen atoms, they emit red, a bluish teal, and then two different types of purple light. Okay? So the task given to the students was, hey, find me something that explains why just these three colors, or four colors if we want to count the two different kinds, and why not others? Why no orange? Why no yellow? Why no green? Why just this one type of red, just this one type of blue teal? What's going on? Now, one of the groups came up with this. Sometimes four hydrogens come into a clump, and that causes red light. Sometimes they come into a clump of three, causes blue light. Sometimes they come into clumps of two, and that causes the purple light. We can look at that and go, hey, that's wrong, right? But what's more valuable is to look at, does this explain the components of what we saw in the question? Would this show us why we saw just these three colors, just these four colors, and not the others? Potentially. Right? Now maybe you're thinking, well, what about, yes, absolutely, those are great questions and good to think about. Let's look at another group and what they did. So this group did, when the hydrogen particles are moving slow, and this is as they have the 10,000 volts, so slow being relative to when you're being electrocuted. But when they're moving at a slower speed, they give off a certain color of light. When they're moving at a faster speed, they give off a different color. So maybe red is at a certain speed, blue is at a higher speed, and purple is at a even higher speed than that, or maybe that's flipped. And so again, we know certain situations where this is obviously not true, so we could say this is wrong. But the question is this useful? And I would argue that in introduction to what's going on with emission spectra hydrogen, this is very useful, because this emphasizes the abstract quality that I'm looking to get across to students. If I say that this is the case, then the question becomes, why is there no orange, why is there no yellow, why is there no green? Well, that must mean that these particles are only moving at certain speeds. There's a blue speed, there is a purple speed. I know I'm mixing the colors up, sorry about that. But it gets the idea of quantization across. And so even though there are flaws that we would say, oh, that's not true, like different particles are always bumping into each other and changing speeds, it does get across an idea that's really pertinent. Now we can correct this and say, actually, it's not just the whole particle itself that's moving at a quantized speed, it's the position and motion of the electrons that's in these quantized motions and existences that allows us to have only certain types of light and not others. And so from this quote-unquote wrong answer, we're able to derive a lot of information. And so it's not really productive for me to sit here and say whether this is right or wrong. It explains what we saw. Now, if I translate this to another situation, all of a sudden I'm going to run into problems where this doesn't explain what I saw. And so looking at the limitations of when does this work, under what conditions and assumptions, what is my system, what are my surroundings, what are my conditions, what are my assumptions about what is true, what other experimental evidences can I draw from, then all of a sudden we start to see issues with this. Now, one of the ways that we could explain this is with the Bohr model. And the Bohr model works very well for hydrogen, right? So if I want to describe the spectral emission spectra of hydrogen, I can use the Bohr model to a pretty precise degree, and it'll function pretty well. Now if I start to get into some other components of that, I might run into some issues. So to say that the Bohr model is right or wrong, not very helpful, but to say when is the Bohr model useful and when is it not useful, now all of a sudden we start to have some good discussions. As soon as I add another electron, the Bohr model starts to fall apart. But why? Okay, well now I can get into the logistics of what might not be functioning within that. So what I want to say is that anything that you do, any answer that you give, any explanation that you give, is going to come with a set of conditions. It's going to come with a set of assumptions. And in education and learning, it's critical that you spend time exploring what those are. So if a teacher tells you this is something, this is the correct answer, when? And assuming what? And that sometimes students start to just accept that the teacher said, oh, because the teacher said. And that's not a healthy, productive way to go down. So here are some comments that I hear from students or from teachers that are complaining about, students being resilient towards having to think hard. My teacher doesn't answer my questions, they never teach, they just say, oh, that's an interesting question, and they walk away without telling me the answer. How am I supposed to know if I'm doing this correctly? So with these ideas, you have students that have become reliant on the authority of their teacher to confirm or deny that their idea is correct. And instead of that, what we want to do is build students that are better able to grapple with when is this true, when is this not true, to trust that they have the confidence and ability to do that analysis. And so because we spend so little time looking at the underlying conditions of things within school, we end up with people who are susceptible to propaganda, right? And we're seeing that right now, where people are like, oh my God, this is outrageous, and yet they'll still go along with it because they have so little experience digesting and going through this analysis. And so I don't want us to start by saying things like, we value mistakes, because the idea that it's just a mistake and it's just this binary right or wrong thing is going to take us down a road where we don't get to do that level of analysis. Now, some people would say, well, at some point you have to draw a line and say this is right or wrong. 2 plus 2 is 4. 32 grams of oxygen is 1 mole. 6 times 4 is 24. And we'll get to that one later. And there can be some agreed upon conditions that are reasonable, and we can know that, like, okay, if we really wanted to get into it, we could find some loophole out of this. This isn't about trying to argue that your test full of wrong answers is giving you an A. What it's trying to say is that you should be evaluated on your ability to analyze and evaluate the conditions and systems that you're putting into that test, more so than just what is the right or wrong answer on. Now, 2 plus 2 is 4 if you do some conditions and assumptions. However, if I take x equal to 1 and I square this side and I cube, oops, I'm sorry, let me try that again. So if I take x equal to 1, then x squared would equal x cubed. Apologies for not getting this right away. Those two things are equal. 1 squared equals 1 cubed. If I subtract 1 from both sides, then those would still be equal. And you can go ahead and double check my math on this, but I assure you this is correct. I can pull this together to make x plus 1 times x minus 1. This comes out to this. And on this side over here, I can do x squared plus x plus 1 equal to x minus 1. This is equal to this. Go ahead and double check me if you like. We have an x minus 1 on both sides. We can cancel that. And we end up with x plus 1 equals x squared plus x plus 1. X is 1, so we have 1 plus 1, which is 2. And x squared plus x plus 1, 1 plus 1 plus 1, which is 3. Now, if 2 equals 3, then I can plug this in and say that 2 plus 2 equals 5. Or I could say 2 plus 2 equals 6. Or really, I could do anything. Now, there's a flaw in this. There's a condition that we don't normally adhere to. And it's that when I canceled those two things out, I was dividing by 0. So we've set up a system of mathematics that relies on numerical consistency by doing that assumption. But if I eliminate that assumption, well, now all of a sudden my rules change. And now all of a sudden, this isn't necessarily true. Or maybe there's something behind what I'm evaluating here that's going to be pertinent. And so even with things that are very obviously true, there's always going to be some level of lack of truth among them. 32 grams of oxygen is 1 mole. Well, it depends. If it's oxygen that's diatomic oxygen, sure. If it's ozone, no. If it's monatomic oxygen, no. So how we work with this, or maybe if I'm looking for a really precise amount, maybe that's not going to work exactly. 6 times 4 is 24, but if that was 6 centimeters times 4 centimeters, well now I might evaluate that and say, you know what, I'm going to round according to sig figs to make this 20 centimeters squared. And so 6 times 4 is not 24. So the conditions and assumptions that we make are really important and critical, and so when we define things as either a mistake or correct, we lose the ability to get into this. And it's a really critical thing, especially in science, but really just in everything that you learn, that you're constantly evaluating and questioning and doing that type of learning that's deep within that. And so when teachers start off by saying, in this class we value mistakes, they take you onto a path that you shouldn't want to go. Okay, let's actually strike the centrifugal force here. But I wanted to kind of end and say, if you're a student, don't sit there and think that all the things are binary. If your teacher says this is the right answer and this is the wrong answer, there are conditions behind that. And sometimes those conditions are so technical and unnecessary that it's fine to just kind of accept them. Sometimes it's not. And if you're not spending any time exploring when it is and isn't in your classrooms, then that's something that you want to take on yourself to become better educated. And if you're a teacher, you want to make this explicit. They're like, hey, maybe we're not going to go down the wormhole every single time, but some of the times we are. And make it clear that we want to constantly be looking for what assumptions and underlying conditions are we making, because it enhances the ability to really look at the rationalization and reasoning behind when this thing works and when this thing doesn't. That really makes us valuable. And back in the 1940s, 1950s, 1930s, we would see in science books this idea that you had to support your claim with lots of evidence. And then we transitioned to a point where textbooks became just claims. And so a lot of us are kind of stuck in this mode where we're used to just having an authority say, this is what's right and this is what's wrong. And instead, in education, we want to push back on that. And when we say things like, you know, let's play our mistake game where everyone makes a mistake on purpose, we're actually reinforcing that flawed idea in the first place.